July 3, 1938. Stoke Bank, Lincolnshire. The steam pressure gauge climbing past operational limits would either validate or destroy everything British railway engineering had promised about high-speed rail travel. Sir Nigel Gresley's LNER Class A4 Mallard was approaching speeds that German and American engineers had declared physically impossible for steam locomotives. The streamlined locomotive had been accelerating down the gradient for 17 minutes, its revolutionary design challenging every assumption about steam power limitations. Traditional British locomotives topped out at 90 miles per hour before track vibrations and mechanical stress forced engineers to throttle back. German streamliners like the BR-05 had reached 118 miles per hour under controlled conditions, but European experts insisted that 120 miles per hour represented an absolute ceiling. Beyond that point, steam engines would literally shake themselves apart. Yet Mallard was pushing past 125 miles per hour while Gresley's team monitored every gauge and structural stress point. In the next 60 seconds, either British engineering would claim the world speed record for steam, or catastrophic mechanical failure would prove the skeptics right. The Great Depression had devastated Britain's railway industry. Passenger numbers dropped 40% between 1929 and 1933 as automobiles and buses captured short-distance travel. The London and North Eastern Railway faced bankruptcy while competing rail companies slashed services and laid off thousands of workers. Britain's once dominant position in railway technology was slipping to Germany and America, where aggressive modernization programs were producing faster, more efficient locomotives. Gresley had watched this decline with the frustration of an engineer who understood that steam power hadn't reached its limits. It had simply stopped evolving. His position as chief mechanical engineer gave him authority to pursue radical designs, but the liner's precarious finances meant every innovation needed to justify its cost through measurable performance improvements. The streamlining concept that would define the A4 class emerged from wind tunnel testing at the National Physical Laboratory. Gresley's team discovered that traditional locomotive shapes created massive aerodynamic drag at high speeds, the blunt smokebox front and exposed running gear acting like air brakes that consumed engine power without producing useful work. German engineers at the Reichsbahn had reached similar conclusions, wrapping their BR-05 locomotives in streamlined casings that reduced wind resistance by 35%. But German designs prioritized appearance over function, adding decorative elements that increased manufacturing costs without improving performance. Gresley needed streamlining that served pure engineering purposes, every curve and surface contributing to reduced drag and improved stability. The resistance came immediately from Britain's conservative railway establishment. The Institution of Mechanical Engineers published papers arguing that streamlining was continental showmanship, unsuited to practical British operations. Critics pointed out that streamlined casings made maintenance difficult, hid mechanical problems from visual inspection, and added weight that reduced locomotive efficiency. More fundamentally, senior engineers questioned whether steam locomotives should even attempt high-speed operation. Electric and diesel power seemed destined to replace steam within decades. Investing in advanced steam technology struck many observers as refining obsolete machinery rather than embracing the future. Gresley's design office in Doncaster became the center of Britain's most ambitious locomotive project in March 1935. The A4 class specifications challenged conventional wisdom about steam engine construction, combining streamlining with boiler innovations that would either revolutionize rail transport or waste resources the LNER couldn't afford to lose. The wedge-shaped front end represented months of wind tunnel research translated into practical metal forming. Unlike German streamliners that applied cosmetic fairings over traditional frames, Gresley integrated aerodynamic shaping into the locomotive's structural design. The result reduced frontal area by 18% while directing airflow smoothly over the boiler rather than creating turbulence that increased drag. Herbert Spencer, Gresley's senior draftsman, had initially resisted the radical departure from proven designs. His 30 years of locomotive experience told him that exposed running gear allowed maintenance crews to spot problems before they caused breakdowns. Covering everything with streamlined casings seemed to prioritize appearance over reliability. "We're hiding the machinery," Spencer argued during early design reviews. "How will depot engineers diagnose issues when they can't see the valve gear operating?" Gresley's response focused on performance data rather than theoretical concerns. Wind tunnel tests showed that exposed cylinders and connecting rods created drag equivalent to pulling an additional freight car at 100 miles per hour. That wasted energy translated directly into reduced speed and increased coal consumption, costs that accumulated across millions of operating miles. The boiler design pushed steam pressure to levels that conservative engineers considered dangerously high. At 250 psi, the A4's working pressure exceeded standard British practice by 30%. Higher pressure meant more power from the same amount of coal, but it also stressed boiler tubes and firebox stays in ways that could lead to catastrophic failures if materials or construction methods proved inadequate. Oliver Bulleid, who would later design his own controversial locomotive classes, questioned the pressure specifications during technical reviews. "We're operating at the margins of material safety," he warned. One boiler failure at high speed could kill the entire crew and discredit streamlined steam for a generation. The solution came through metallurgical advances that British steel manufacturers had developed for marine boiler construction. High-tensile steel alloys could handle the increased stress while maintaining safety margins that satisfied even cautious inspectors. But the specialized materials added costs that made each A4 locomotive 15% more expensive than conventional designs. Financial pressure intensified when the LNER board questioned whether faster passenger service would generate enough additional revenue to justify the development expenses. Railway economics in the 1930s favored operational efficiency over speed records. Freight traffic provided stable income while passenger services struggled against automobile competition. Gressley argued that high-speed capability would transform the laner's competitive position. Express trains between London and Edinburgh could match automobile travel times while offering superior comfort and reliability. But he needed to demonstrate that steam locomotives could actually achieve the sustained high speeds his projections assumed. Speeds that no British engine had ever maintained in regular service. The first A4, Silver Link, emerged from Doncaster Works in September 1935. Its sleek silver-gray livery made it look fast even standing still, but the true test would come during proving runs where performance data would either validate Gressley's engineering vision or expose fatal design flaws. The technical breakthrough that would make record-breaking speeds possible emerged from an unexpected source: French locomotive designer André Chapillon, whose work on exhaust systems had revolutionized continental steam engineering. Gressley recognized that British locomotives were choking on their own exhaust gases, limiting power output regardless of boiler capacity. Traditional single-chimney designs created a phenomenon engineers called back pressure. Spent steam from the cylinders couldn't escape fast enough, creating resistance that reduced engine efficiency. At low speeds this hardly mattered, but at 100 miles per hour the exhaust restriction consumed power that should have been driving the wheels forward. Chapillon's solution divided the exhaust stream between two chimneys, each with its own blast pipe that accelerated gases out of the smokebox. The double chimney arrangement reduced back pressure by 40% while improving draft through the firebox, pulling more air through the burning coal and increasing combustion efficiency simultaneously. British railway engineers viewed the French innovations with predictable skepticism. "Continental complications" was the dismissive phrase that appeared in technical journals, suggesting that British single-chimney practice represented superior engineering judgment rather than conservative reluctance to adopt proven improvements. Gressley tested the double-chimney concept on an experimental A4 in 1937. The performance gains were immediate and dramatic. The modified locomotive pulled heavier trains at higher average speeds while consuming less coal per mile. The exhaust improvement transformed the A4 from an impressively fast design into a machine capable of sustained high-speed operation. The modification affected more than just exhaust flow. The improved draft allowed firemen to maintain higher steam pressure with less physical effort, reducing crew fatigue during long express runs. This operational advantage mattered enormously for practical service, where crews needed to sustain performance across 4-hour shifts rather than brief demonstration runs. Implementation required retrofitting the entire A4 class with new chimneys and blast pipes, an expensive program that the LNER board approved only after seeing undeniable performance data. The modified locomotives entered service throughout 1938, their distinctive twin exhaust streams visible proof that British engineering could adopt continental innovations when results justified costs. The timing proved crucial. By mid-1938, German railways were promoting their streamlined BR-05 locomotives as the world's fastest steam engines. The Reich's propaganda machinery presented high-speed rail as evidence of German technical superiority, with newsreels showing streamliners racing through the countryside at speeds British railways supposedly couldn't match. This competitive pressure gave Gressley the political support needed for a formal record attempt. The Laner's management recognized that international prestige had commercial value. A British speed record would generate publicity worth far more than the attempt would cost. Railway enthusiasts across Europe followed high-speed developments with the same passion modern audiences reserve for motorsports. Gressley selected Mallard for the record run based on its recent double-chimney installation and optimal mechanical condition. The locomotive had accumulated sufficient service miles to work through any initial issues, but remained new enough that all components were within their design life. The engine's running gear had been precision balanced to minimize vibration at extreme speeds, a process that required days of careful adjustment. Everything pointed toward early July as the optimal window for the attempt. Summer weather would provide maximum visibility and minimal track moisture. The Stoke Bank gradient offered sustained downhill acceleration. All that remained was executing a plan that pushed steam technology beyond any previous limits. The announcement of a formal high-speed record attempt triggered immediate warnings from Britain's engineering establishment. Sir William Stanier, chief mechanical engineer of the rival LMS Railway, publicly questioned the wisdom of risking lives and equipment for what he termed publicity stunts with no operational value. Stanier's concerns reflected genuine safety considerations. At speeds above 110 miles per hour, steam locomotives entered unknown territory where traditional engineering calculations might not predict structural behavior accurately. Track quality varied unpredictably along any given route, with joints and switches creating momentary irregularities that could derail locomotives at extreme velocities. The Institution of Civil Engineers commissioned a report examining high-speed rail safety. Their conclusions emphasized the gap between theoretical design limits and proven operational experience. Steam locomotives had evolved through incremental improvements over a century, each generation slightly faster and more powerful than the last. Attempting to jump directly to 125 miles per hour ignored the cautious progression that had kept railway safety records relatively strong. More specific technical warnings focused on wheel balance and reciprocating mass. At 120 miles per hour, the A4's driving wheels would rotate 7.2 times per second. Any imperfection in wheel casting or tire mounting would create vibrations that increased exponentially with speed. Those vibrations could shatter wheel centers, fracture axles, or cause trucks to lift off the rails during momentary track irregularities. The reciprocating motion of pistons, connecting rods, and valve gear created additional dynamic loads that stressed every component in the running gear. Traditional steam locomotives had visible oscillation at 70 miles per hour, the entire engine rocking rhythmically as counterweights attempted to balance reciprocating masses. Engineers feared that at 125 miles per hour those oscillations would become violent enough to break coupling rods or bend main frames. German experience with high-speed attempts supported these concerns. During a 1936 test run, a BR-05 locomotive suffered catastrophic bearing failure at 118 miles per hour. The accident destroyed the locomotive's middle driving axle and derailed 3 passenger coaches. Only the driver's quick response prevented fatalities, but the incident demonstrated that pushing steam locomotives beyond design limits carried real risks. Insurance companies responded by refusing to cover the planned record attempt under standard railway policies. The Eleanor would be self-insuring against any damages, injuries, or equipment losses, a financial exposure that worried the company's directors even as they approved Gressley's plans. The track section chosen for the attempt raised additional concerns. Stoke Bank's 1 in 200 gradient provided acceleration assistance, but it also meant that any loss of control would be nearly impossible to recover from. The 3-mile descent offered limited opportunities to brake if something went wrong at maximum speed. Railway union representatives demanded assurances that crew participation would be voluntary and that families would receive compensation if the attempt resulted in fatalities. The formality of these negotiations reminded everyone involved that record-breaking carried measurable danger. This wasn't theoretical engineering but practical risk-taking with human lives. Gressley absorbed all the criticisms and warnings while continuing preparations. His confidence came from detailed analysis rather than optimism. Every component on Mallard had been inspected, measured, and evaluated. The locomotive represented the best engineering British Railways could produce. If steam power had any remaining potential, this attempt would reveal it. The morning of July 3, 1938 began with meticulous preparation at Grantham Depot. Mallard's crew, driver Joseph Duddington and fireman Thomas Bray, arrived before dawn to supervise the locomotive's final inspections. Every bearing had been freshly packed, every moving part lubricated to specifications that eliminated any friction that might limit performance. The test train consisted of 7 coaches carrying LNER officials and railway journalists equipped with recording instruments. Dynamometer car number 9 would capture precise speed measurements throughout the run, providing data that would either substantiate or discredit any record claims. Unlike earlier speed attempts where estimates varied widely, modern instrumentation would deliver irrefutable evidence. Duddington had been selected for his exceptional throttle control and his intimate familiarity with the Stoke Bank route. His 32 years of locomotive operation included thousands of hours at the controls of express passenger trains. If anyone could sense impending mechanical trouble through subtle changes in engine behavior, Duddington's experienced hands would detect the warning signs. The northbound run to Barkston provided opportunity to bring Mallard up to operating temperature gradually. Steam pressure stabilized at 245 psi while boiler water levels remained steady, crucial indicators that all systems were functioning normally. At Little Bytham, 20 miles from Grantham, Duddington opened the regulator and began serious acceleration. The gradient initially worked against them as the train climbed towards Stoke Summit. Speed increased steadily through 80, 90 and 100 miles per hour as the A4's powerful cylinders overcame track resistance and aerodynamic drag. Mallard's streamlined casing was performing as designed. Airflow remained smooth over the boiler without the turbulence that plagued conventional locomotives at high speeds. Crossing Stoke Summit at 105 miles per hour, the descent began. Gravity now added its force to steam power, and Mallard's acceleration became dramatic. The speedometer needle swept past 110, then 115 miles per hour as track miles disappeared beneath the racing wheels. Inside the dynamometer car, recording instruments traced curves that represented speeds no British locomotive had ever achieved. At 120 miles per hour, Duddington felt vibrations beginning to build through the footplate, not the catastrophic oscillations that engineers feared, but rhythmic pulsations that indicated the locomotive was reaching its mechanical limits. The wheel balance that had seemed perfect at normal speeds was creating harmonic effects at extreme velocity. The speedometer touched 123, then 124 miles per hour. Duddington maintained full regulator, trusting Gressley's engineering as Mallard pressed toward the absolute limit of steam locomotive capability. For 25 seconds the speed held steady at 125 miles per hour, already a British record and matching the German BR-05's unofficial maximum. Then, impossibly, the needle climbed higher. 125.5 miles per hour. 126 miles per hour. The dynamometer car's precise instruments recorded the peak speed as 126 miles per hour, a velocity that contradicted every expert prediction about steam power's limitations. The record lasted only seconds before Duddington began braking for the upcoming curves. But those seconds had demonstrated that properly engineered steam locomotives could exceed speeds that conservative experts had declared physically impossible. Mallard had proven that innovation could overcome conventional wisdom when design excellence met operational skill.